This is a production of Cornell University.
Okay, so we've been talking about soil water for the last couple lectures, and if we're going to be talking about soil water, it makes sense for us to start talking about soil air. Okay, we also introduced with soil water this idea of the redox potentials and issues of respiration and the effects of water. Well, let's actually talk about how that directly relates to the air component and redox potential there. All right, so you have seen this slide, parts of this slide for a couple times, but basically we're talking about the soil system. So we're talking about a three-phase system. We got the solid part, mineral material and organic material. We also have the liquids and the gases. Okay, so we've got the solids down, we've got the liquids down. Let's actually start talking about the gases. Okay, when we talk about soil air, often people just think of the oxygen, but we're really talking about the whole atmospheric system, much like the atmospheric system that we breathe. You know, what is it? Very small percent of it is actually oxygen. Okay, most of it's nitrogen, right? Okay, well, the truth is that's what's going on in the soil atmosphere as well. But in the soil atmosphere, respiration's happening just as it is up here, but in the soil atmosphere, respiration is in a restricted area. It's in a restricted zone. So one would think as things happen in that area, that pores, that the gas composition of the soil air is going to be different than the gas composition of the atmospheric air up here. Does that make sense? Okay? And so if we look at that, obviously things are eating down there. And if they're eating, they're consuming oxygen and they're producing CO2. Because the CO2 is being produced down underneath the soil, for that oxygen to be replaced, the CO2 actually has to come out and the oxygen has to come in. Okay? And that's why you have these gradients. So this is why you have this change in concentration of gases in the soil atmosphere versus up here. Okay? This is just a chart to sort of give you an idea about what that composition looks like. And it's not dramatically different. But it's different enough, just a little bit, it's different enough to actually create some real changes in how the atmosphere is being used. Okay, so here's the gases: nitrogen, oxygen, CO2. Soil air versus the atmosphere. Nitrogen, a little bit less. Okay, there's a little bit more nitrogen in the soil atmosphere. O2, 20% down there, 20.9. But look at the CO2 concentration. Dramatic increase in CO2 down below. Okay, now I think my next slide is a good example. Okay, this is why. Okay, so if this is the soil pore and down here is where all the things are being respiring, okay, for that CO2 to get out and for oxygen to get in, because there's no photosynthesis down here. There's nothing producing oxygen down here. It's all being produced up here. So for that oxygen to get in, the CO2 has to exchange. Okay, and that exchange is really controlled by diffusion. Okay, so air movement within the air is basically controlled by two processes. One is diffusion and one is mass flow. Mass flow is a little bit less important. We'll talk about it for a moment. But diffusion is really what's driving most of this exchange. Okay, the rate of diffusion basically depends on four things. And if I'm going too fast, slow me down. Sorry, it's Friday, I'm on a race. Okay, the first is soil water content. That was our last two lectures, right? How much water is in this volume of pores is going to affect how fast the gas exchanges. Gas exchanges very quickly up here in the air. There's not a lot of molecules in this volume of room. But if I fill this room with water, the gas exchange would slow down. The molecules would move slower. Okay, they would run into things. They'd run into more things and you'd start seeing bouncing around. And that would slow the distance traveled with each tangent. Does that make sense? Okay, so how much water is in the soil is going to affect that exchange rate. The size and the number of the pores. Okay, here is one large pore. This room is one large pore. But the same volume in soil, lots and lots of pores, small. So the pathways for that exchange are greatly restricted. The continuity of those pores is extremely important. If I have a pore that goes way up here and it stops right here, any kind of gas that's exchanging up in here is just going into a dead end. It has to come back out and find a pore all the way up to the atmosphere, above the air atmosphere. Okay? And then finally, the temperature. Why is temperature important? This is not the C10 rule. Why is temperature important? We're getting into the heating season of the year, right? Or you can think of this in the middle of the summertime. Anybody have a room on the top of the house? It's the hot part of the house, right? What happens to air when it gets hot? It rises. Now, if I have hot air up here and cold air down here, do you think there's a lot of impetus for that hot air to be rising from here? Because the air is up here is already hot. Okay? So that temperature plays a big role in that exchange. Okay? And that's diffusion. Now, we also have mass flow. To a certain extent, it's less important. I mean, there's some events. But we sort of talked about this when we were talking about water, and we were talking about the Artesian effect. When I've got a pressure gradient coming through, that pressure gradient potentially is going to push or pull, if it's a low pressure versus high pressure, it's potentially going to push or pull through these pores. You know, if I have a high pressure up here and a low pressure here, we're going to see sort of a push this way. On the other hand, if I have a low pressure system coming in, weather-wise, we're going to start seeing an exchange coming out. I mean, this is a glorified example of a cave. You know, you go into caves and there's breezes. That's basically what we're talking about. Okay, cool? All right. All right. So, now I said that we're going to be talking about air, but we're going to take a step back and we're actually going to talk about water for a little bit, but we're going to be talking about water in the context of air. Okay? Saturated soils quickly become deficient in O2. Now, O2 is not necessarily air, but it's part of that air, that soil air. The question is why? Why do saturated soils quickly become depleted in O2? What's going on down there?
Gas exchange is slow and the water is displaced.
Okay, so gas exchange is slow and water can potentially replace the oxygen, so oxygen and everything else that's in the soil atmosphere can be pushed out. Okay, so that's one. Okay, that's an exchange where we have an increase in water. Okay, but let's say we have the water there already. Okay, water levels are not changing. We are still going to see a loss of oxygen. Why?
Things are respirating and there's no more oxygen coming into them.
If no more oxygen is exchanging into the system, and things are respiring, they are aerobic aspiration. You know, we're oxygen breathers. Okay, versus anaerobic systems. If they're breathing, they're using up VO2. So just by respiration, the O2 levels are going down. And if the system is saturated, let's go back to the argument over here. If the system's saturated, the exchange rates are going to dramatically drop. So as a result, we're going to have this depletion in O2. Okay? Good classic example of this. You've seen these. These are basically, we're looking at thetas here. So this is the fraction of the total soil volume that's occupied by air versus PT, which is the total volume. That's the porosity. That's the pore space. Versus the theta. Theta is how much water is in the system, right? So if you basically look at a theta of 0, the system's totally dry. Maximum exchange. You start getting to a theta where I'm 50% saturated, or 25% theta. The volume has 25% water. Okay? We're dramatically slowing down. I mean, I drew the blue lines in there. I know it's pretty bad. But, you know, the exchange of that oxygen is going to be dramatically reduced. And that's basically that story, why it's being reduced. Okay, not only are the plants respiring, but if that system goes anaerobic, what's going to happen to those organisms? They die. Okay? And if they die, all of a sudden you have more food down there. Okay? You don't have the organisms that are doing the aerobic respiration, but then you start seeing the decomposition by anaerobic processes. And that in turn is going to dramatically change the composition of that soil atmosphere.
This has been a production of Cornell University, on the web at cornell.edu.